All right, we are ready for step 3, which is extending phi z to the rationals. And after we went over the last step in so much detail, I think that we should be getting comfortable with isomorphisms and the embeddings and how to prove the addition and multiplication and well-defined onto and one-on-one, so one-to-one. So I think we'll be able to go over this one a lot faster than I did last time. And in addition, the longest part might be simply defining rationals. And the really interesting thing about this, if you haven't watched the integer one yet, watch the integer video, the last video, because it's quite interesting to me how similar the integers and the rationals are. It really is like the multiplication over rationals is almost the same thing as addition over the integers. They're defined so similarly, and multiplication in rationals is even defined the same way as addition in integers. But then after that, they get a little bit, there's some little subtle differences that have to do with not dividing by 0 and things. So we're going to construct the rationals as equivalence classes of ordered pairs, A, B, with A and B elements of the integers this time, and of course, B not equal to 0. If I ever forget to mention that, just remember that always the denominator cannot be 0. So this is exactly how we defined integers, as pairs of natural numbers, as equivalence classes of pairs of natural numbers. So we define the equivalence class as A, B, and CD are in the same equivalence class. That is A, B, CD, if and only if AD equals B, C. That's exactly how we defined integers with, it was A plus D equals B plus C. So you just multiply the outside ones, multiply the outside ones and multiply the inside ones. So with this definition, then we're just calling, of course, AB is A over B. That's what A comma B equals. So this is just the equivalence class. It's a pair of integers. We just write it as A over B. That's what we mean by rational numbers. And so the operations on rationals also follow the standard form with this definition. So ordering of rational numbers, A over B is less than C over D if and only if AD is less than BC. This is exactly how we defined ordering in integers as well, except it was addition instead of multiplication. So there's one slight issue here, which is that multiplying by a negative number switches the ordering of the inequality. So what we do is, in order to deal with that, if the denominator is negative, we just move that denominator to the top. So if B is negative A, then we just rewrite that as negative A over B. Okay? If B is negative, we change the sign of both of them. So if you take the inverse of B, it's the same as if you take the inverse of A. But what we really mean is that if B is negative, then we're gonna change the sign of both of them so that B is positive and A is negative. The reason we do that is now, if the denominators are positive, then you can multiply both sides. You're only multiplying by a positive number, so the inequality stays the same. If B was negative, you'd have to switch the inequality and it would get a lot more messy. So this is just neater. Okay. For addition, the definition of addition is sort of the strangest one of these. If you're just looking at them as ordered pairs and equivalence classes, this is a very odd definition. But A over B plus C over D equals AD plus BC over BD. Something that you might want to think about, that it's been in my head, but I haven't really spent a lot of time thinking about it. But could we do something like this for integers and addition as well? What would it mean if we used plus and had this extra bit with the second numbers? So it's a very odd difference from what the integers are. But that's addition. Multiplication is A over B times C over D equals AC over BD. And again, this is also the same definition that addition was for integers. If you're adding two pairs of for integers, it's a plus c comma b plus d. Here it's a times c comma b plus d. So this would equal ac b d. Then the other interesting thing about rational numbers is that we're used to thinking, we have notation for thinking about the pair, but with integers we don't. It's a lot more comfortable to just think of a fraction in this way rather than as a pair. With integers, there's no standard way that you can look at all of them in this way, because if it's negative or positive, which one's bigger, then sometimes they're, if it's 0 comma n, then that equals minus n, right? But then n comma 0 equals n. So there's no uniform way of doing it like we have for rationals. It's also interesting to think about whether we could come up with a notation for integers that was more symmetric than this, that encapsulated all of them rather than having to have this rule. So anyway, that's all integers, never mind that. And then finally, inverse. So the additive inverse of a fraction is called its opposite. And again, we just put the minus in the numerator. So we take the additive inverse of a over b. The multiplicative inverse is written a over b to the minus 1 equals, of course, b over a. And so notice we didn't need to worry about what a multiplicative inverse of integers was because they don't have them, right? Because they have to have fractions, which is why they're not a field and rational numbers are a field. So rational numbers actually have two sets of inverses, an additive inverse and a multiplicative inverse. Integers don't. Okay, so that's it. We've defined all of the operations now. Now it's time to embed them into the reals. So for all a and b in the integers, with b not equal to 0, or you could also say for all a over b in Q. So the embedding into X of a over b is the embedding of the integer a times the embedding times the inverse of the embedding of b. Put one more. So this again is exactly what the integers looked like, except it was an additive inverse instead of a multiplicative inverse. And then y, of course, is the same. Okay, and this is the embedding of the rationals. We're defining it in terms of the embeddings of the integers, because a and b here are integers. So this is our embeddings of integers into x and y. Then you multiply them in x and y times the multiplicative inverse in x and y, and that's how we define embedding the rationals into x and y. So of course, the rationals embedded into x are qx, and embedded into y are qy. So we just have to quickly look to make sure that these are well-defined, one-to-one and onto, and it's actually obvious, but just to make it explicit. So since a over b is the definition of any rational, then this clearly covers all of the rationals. So it's clearly onto. And since a and b are equivalence classes, then it's also clearly one-to-one and well-defined, because if ab equals cd, then e of x of a is going to equal e of x of c, e of x of b is going to equal e of x of d, and so on. So it's clearly one-to-one and well-defined as well. Okay, so just notation, one last thing. So if m equals the embedding of a and n equals the embedding of b into x, where a and b are elements of the integers, then a rational number in qx can be denoted m over n, okay? So this is, we've sort of already said this, but we're just being explicit that this is now how we're denoting an integer in qx. Above we were talking about rationals about fractions in the rationals. Now we're talking about how we call fractions in the rationals embedded into x. They're not the same set. That's sort of what we're showing, is that they're isomorphic and that they're embedded in a straightforward way. So all of the following are equivalent. So we have m over n, that's just a regular fraction. We have the division sign, that's the same thing. We can say that e to the a is divided by e of b. And then that equals ex of a over ex of b. And that equals ex of a over b. So these all mean the same thing. And I mean, a lot of them are just obvious, but just different ways of saying the same thing. Okay. Now, the isomorphism. So this is the isomorphism of the rationals embedded in x and rationals embedded in y. So we're showing that there's an isomorphism between them. So what we're going to do is extend our map of the integers. So we're going to use our map of the integers to define a new map of all rationals. So let m and n be elements of zx with n does not equal 0, then m divided m, n, is in qx. So we define, so we extend phi of z to phi of q by setting phi of q of m over n equals phi of z of m over phi z of n. This again is exactly the same way that we defined, that we extended phi of the naturals to phi of the integers by saying that the equivalence class in z was equivalent to the equivalence class, or the isomorphism of the naturals, and then with the isomorphism of the naturals, right? So here we're doing the same thing. This is an equivalence class, this is an equivalence class. So if we have two integers in z of x and we map them to y, we do that by mapping m into y and mapping n into y, and then we're making the equivalence class of those. In other words, a fraction of those. That's the map. So we have to show that this map is an isomorphism. So first, same thing as before, we have to show that it's well-defined one-to-one and onto, and then we show that it preserves addition, multiplication, and ordering. So first, well-defined. And again, all of these proofs are gonna mirror integers very closely. So first of all, in order to prove it's well-defined, remember that there's this problem with fractions, which is that the denominator cannot be 0. So we just need to make sure that phi of q never accidentally sends something to 0. So we just need to point that out. And it's clearly true because we know that phi of z is 1-to-1, so that if b does not equal 0, then phi sub z of b does not equal 0, right? Because phi z of 0 equals 0y, right? And if it's 1-to-1, there can be no other integer that's going to go from x to 0 in y. So anything in z of x that is not 0 must go to something other than 0 in z of y. So we have to show it's well defined. That means that if x equals y, then f of x equals f of y. So we start with we have two fractions, a over b and c over d, for any a, b, c, d elements of z with b, d not equal to 0. I think I'm gonna have to go to a new page. I don't quite have enough room. So a over b equals c over d. So if we just apply the definition of fraction equivalence, then that means that AD equals BC. And we know that phi sub z is well defined. That means that phi z of AD equals phi z of BC. And then we know that phi z, we just proved this last time, preserves multiplication. So this equals phi z of A times phi z of D equals phi z of B times phi z of C. This, AD times BC, this is just the definition of fraction equivalence in Y. So these are in Y. So that means that phi z of A over phi z of B equals phi z of C over phi z. You can see what we did here. We just multiplied both sides by 1 over d, and then multiplied both sides by 1 over b, right? So you cancel those, move them over. And this is the definition of our map in Q. So that means that phi z of A over phi z of B is the definition of phi Q of A over B, phi Q of C over D. So that's what we needed to prove. We started with AB equals CD, and we showed that if AB equals CD, then phi Q of AB equals phi Q of CD. So it's well defined. Okay, I'm going to try again to do this on one page. So 1 to 1. 1 to 1 means sort of the opposite of well defined, that if f of x equals f of y, then x equals y. So we basically just start the other direction. It's basically just the same proof backward. If I just start with phi of q a over b equals phi of q c over d, I'm just going to read this backwards, and you can see that it's the same thing. So if we just use the definition of phi of q, we get phi z of a over phi z of b, phi z of c over phi z of d. We take that, the definition of fraction equivalence is you just multiply both denominators, cross multiply them, and we have AD equals BC. Then using, from here, we know that phi z preserves multiplication. So phi z a times phi zd equals phi zad. B and C equals B and C. We know that phi z is well defined, so that and we know that it's 1 to 1, so that if phi z of AD equals phi z of BC, then AD equals BC. Then applying the definition of fraction equivalence again, we get that if AD equals BC, that means that A over B equals C over D. So that's it. So 1 to 1 was easy. Now for onto means that for every y in the codomain, so for every y in Qy, there exists an x in Q of x such that phi Q x equals y. So we just need to show that for every C over D in Q of y, there exists an A and B in Z of x such that phi Q of A over B equals C over D. So we know that phi of Z is onto already. So we know that for every C and D in Z of y, these are CD elements of Z, y. For every C and D elements of D of ZY, there is some A. There's some A and B such that phi of Z of A equals C and phi Z of B equals D. So then that's all there is to it. That means that there's an A over B such that phi Z of A over phi Z of B equals CD. And this, of course, is the definition of phi Q. So we just showed that for any C and D, there is an A and B such that phi Q of AB equals CD. So it's onto. We've shown that it's 1 to 1, onto, and well defined. Okay. Now we just have to show addition, multiplication, and ordering, and we're done. So addition. Let A, B, C, D be elements of ZA with B, D not equal to 0, so that A comma B and C comma D, or C over D, are elements of Q of X. So we need to show that phi Q of A over B times C over D equals phi Q of A over B times phi Q of C over D. All right, just go through it, go down, over, and back, same as always. So phi Q of, oh wait, did I say plus times? Wait, no, I'm sorry, we're doing plus. What am I talking about? Multiplication is next. Plus, same thing. A over B plus C over D. If that's true, so first we define, or we use the definition of fraction addition. So we have phi Q, this equals phi Q of AD plus BC over BD. That implies, now we use the definition of phi Q to go down to Z, which we're already familiar with. AD plus BC over, oh, I'm sorry, wait. No, I'm sorry. We're using the definition of phi Q is phi Z of AD plus BC over phi Z of BD. Now, we know that phi z preserves multiplication, and we know that it preserves addition. So we can rewrite this as phi z of A times phi z of D plus phi z of B, phi z of C, right? I combine two steps because first you can say phi AD plus phi BC, and then phi A, phi D, etc. over phi z of B, phi z of D. Now, this is the definition of fractional addition in Y. So we can rewrite this as simply phi of A, phi z of A over phi z of B plus phi z of C over phi z of D, right? That's what this means. A over B plus C over D equals AD plus BC over BD. Now just apply the definition of phi Q again. This equals phi Q of A over B, and this equals phi Q of C over D. And that's what we wanted. We started with phi Q of AB plus CD, and we showed that that equals phi Q of AB plus phi Q of CD. And I just realized this whole time, and I've been saying implied, but I mean equals. Okay, so new page. Multiplication. Same thing, let A, B, C, D be elements of Z, B and D not equal 0. Same thing. So now we need to show that phi Q of A over B times C over D equals phi Q of A over B times phi Q of C over D. So start with the first one. Whoops. Phi Q of A, B times CD equals, first just apply the definition of fraction multiplication. So it equals phi Q of AC over BD. Now apply the definition of phi Q. It's phi Z of AC over phi Z of BD. Now we know that phi Z preserves multiplication. So phi Z A, phi Z C, phi Z B, phi Z D. Sorry about that. And now this, again, we apply the definition of multiplication again, and we have that this equals phi Z A over phi Z B times phi Z C over phi Z D, and apply the definition of phi Q, and we have that phi Q of A over B times phi Q of C over D. We started with phi Q of A over B times C over D. We showed that that equals phi Q of AB times phi Q of CD. So phi Q preserves multiplication. And lastly, ordering. Same thing, let A, B, C, D be elements of ZX, BD not in 0, or not equal to 0. Need to show that if A over B is less than C over D, that implies that phi Q of A over B is less than phi Q of C over D. This is X, and that's Y. Okay, so first of all, we have to do what we mentioned before. When we're dealing with inequalities, we want to make sure that the denominators are positive. So the first thing we have to do is if B or D are negative, then change the sign of both of them. And we know that A over minus B equals minus A over B. So just switch the signs if either one of these are negative to make the B and the D positive, so we don't have to worry about the inequality. So from there, it should be straightforward. So with both denominators positive, we know that A over B is less than C over D if and only if A D is less than B C, right? Okay, so start with A over B less than C over D. So using the definition, that implies that AD is less than BC. Phi Z preserves order, and these are all integers. So QZ of AD is less than phi Z of BC. Phi Z preserves multiplication. So phi Z of A, phi Z of D is less than phi Z of B, phi z of c, right? So these are both integers, so this is definitely less than this. And then furthermore, we know that phi z preserves multiplication, so I can rewrite it by applying the phi z separately. Now, this is the definition of inequality for fractions in y. So we can rewrite this as phi z of a over phi z of b is less than phi z of c over phi z of d, right? Because that's how you do it. You multiply them out like that. And then we just apply the definition of phi q, and we're done. So this equals phi q of a over b is less than phi q of c over d. And once again, that's what we wanted to prove. We started with a over b is less than c over d in x, and we proved that phi q of a over b is less than phi q of c over d in y. So phi q preserves ordering as well. So phi q is an isomorphism between the rationals embedded in x and the rationals embedded in y. So the next step next week is the hard one. So this one was actually quite easy because it's basically the same thing that we did with integers. Now, once again, the real numbers get very difficult yet again because we're basically using Dedekind cuts and phi and how phi relates to Dedekind cuts, and we have to use supremum. We're going to have to create an entirely new sort of set of things, of tools we can use in order to do this. So to prove the real numbers gets a lot tougher. But what we've proved so far is still already very interesting because we've been nailing things down, right? So we've shown now that the naturals in x lay on top of the naturals in y, same with the integers. Now it's the same with all of the rationals. So the chances that the real numbers are not going to be an isomorphism as well seem very small to me because between any two rationals there's an irrational. But there could still conceivably be some kind of weird twisting in there between two rationals in how the real numbers are defined inside there. So we've got to show that the real numbers are also isomorphic. And then we'll have shown that for any two sets x and y that are ordered fields with the least upper bound property, there is an isomorphism between the two sets. We'll be done with that part, and then there's one last thing we have to prove. Because we're not just showing that any two such sets are isomorphic, we're actually showing that they're the same set, that there's only one isomorphism between them, so that you can say it's the identity automorphism, that you can't rearrange them or twist them in any way. 0, 0, 1 is 1, and everything else is the same as well. Okay, see you next week.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.